Okay, still section 2.2, I guess, and because I realized in the last video where we looked at reflection over a line, I was going to show why it was a line through the origin, and um, so let me do that, but then I'll also look at something called an affine transformation. And so this is no longer a linear transformation, it's an affine transformation. And in an affine transformation, actually, for us, what that's going to be is that our transformation t from r n to rm, well, it's going to have a linear transformation, so t of x. I'll start with a linear transformation, ax, but then I am going to add just some other vector to that. So I'll call it v, and that is an affine transformation. So when you think of your usual y equal mx plus b, we say, oh, there's a linear function and so forth. Yeah, it gets a little messy because, really technically, y equal mx plus b is an affine transformation, not linear, and line through the origin like y equal mx is then the linear thing. So it can get a little messy when you're in there talking about a function from the real numbers to the real numbers, because we do, we'll say, oh yeah, this is, a straight line, a nice linear function, even though it's not going through the origin. So just kind of keep that in mind. But generally speaking, an affine transformation takes that linear part and then we just add a vector to it. Okay, so now getting back to the reflection, right, is a very simple idea that the line really does need to be through the origin, because they said, oh, just take that angle with the axis, and well, let's say I want to reflect over this line, L. And, here's a point. I should get a point right there. But what's the angle with the x-axis? It's 0. The angle is 0. And so, if we look at, remember that reflection was supposed to be, what was it? A was cosine 2 theta, sine 2 theta, and sine 2 theta, and minus cosine 2 theta. Well, here, right, theta equals 0. And so that would be, the matrix 1, 0, 0, negative 1. But at least, if I drew this pretty well, obviously, when I go from this point and reflect it, my y value should be positive. But here, if I take anything with a positive y value, right, this is x times y, here I will get x minus y. And so if I had a positive y value, I'll get a negative y value. It's still reflecting over the whole x-axis. So what's the problem? Well, the problem was this line was not through the origin, and so it needs to be, but that's kind of where the affine transformation comes in. So if I want to reflect over a line like that, right? Okay, so very generally, how about a line like that? And I would like to reflect over this. Well, that's where the affine transformation comes in, is so step 1 is just shift everything down to the origin here, and the easiest way to do that would be to subtract something, whatever this intercept is, from the y value. But I could do it other ways. You know, I could think of it as shifting down this way. So, you know, but we'll call this just, you know, we'll say there's B. So what I'll start with is for my given xy, I'm going to, you know, start with my xy, and I am going to subtract 0b. So see, that's an affine transformation right there, because what I've done is, in this case, A is equal to 1, 0, 0, 1, right? Because when I multiply by this, what we call the identity matrix, I'll still get xy back. But then I've added in, what did I call it back here, V? Yeah. So what I've added then is that I've said V is equal to 0, negative B. And so I've taken A times my vector and then plus this V, or minus 0B. So if I do that first, then you see everything looks like that. And so now if I second do my rotation, so everything's along there and that point's there, you know, so here was a translation, and that's what we get with our affine portion. We translate, we move x and y. Then I did a rotation, and then 3, I'll do my reflection. So I'll get down here, I'll do a reflection. And 4, then I will rotate back. Okay, so I do another rotation. And then finally I undo the translation. And I get my answer. Okay, so if we do that, then you know, kind of in series, I would start with some xy. I would subtract off my 0b. Okay, so there was the 1. Then the 2, I would hit this with a rotation matrix. I'm going to call that matrix R theta, or maybe I'll do A theta. So we'll say A theta for the rotation of theta degrees. In this case, I guess we'll call it negative theta. So now I'm going to multiply my A negative theta times that whole result. So xy minus 0b. So that is a parenthesis. Then 3 was the reflection part, and so we'll call that A sub r. So I multiply that answer, A sub r, A sub negative theta, you know, all times my xy minus 0b. And then undo the rotation. So I get my A theta, A r, A minus theta. Now, the nice part is this part is just that angle portion. And so 0b. And so that is just the cosine 2 theta. So I can write this as this becomes, cosine 2 theta, sine 2 theta, sine 2 theta, and minus cosine 2 theta, and x, y, minus 0b, okay, so that's what we have so far. And then, once I've done that, I just undo it by adding the b back. So, I undo that translation. So here I have my cosine 2 theta, sine 2 theta, sine 2 theta, minus cosine 2 theta, times my xy minus my 0b, and then I need to add back the 0b. Okay, so let's try that with again, I like to go with simple examples just to kind of see, does it look like it's working? Okay, so here's 1. So here's y equals 1. And if I start with the point 2, 1, and I reflect that over that line, I should get 2, 0. Oops, wait. I didn't mean 2, 1, I meant 2, 2. When I reflect that over that line, I should get 2, 0. Okay, now this is parallel with the x-axis, so theta equals 0. And so if I make my matrix, I get cosine of 0, which is 1. I get sine of 0, 0. Cosine of, or sine of 0 is 0, and negative cosine of 0 is negative 1. Okay, and then, oops, I take my original 2, 2, but I have to subtract off b, which is the, the 0, 1 there. And then what I'm going to do is, once I've done that multiplication, I'm going to add back in 0, 1. Okay, so I have 1, 0, 0, negative 1. 2, 2 minus 0, 1 is the vector 2, 1. And so I'll do that multiplication and then add in 0, 1. Okay, so I get 2 and negative 1 when I do the multiplication, plus 0, 1. And that is the vector 2, 0, which is what I thought I ought to get. Okay, so you see, we can still reflect over any arbitrary line in these 2 dimensions. Not a problem. I can do that. But I need this thing called an affine transformation back here, way back here. I need to do the affine transformation to make that work. So I have to first move my line of interest back to the origin. Then, once it's at the origin, I do the regular reflection there using this matrix. And then, once I've finished that, then I need to translate back with what I did. But so, I like these geometric transformations because it does a couple of things. It forces us to think kind of step by step through a problem and kind of continually reducing the problem to something a little different. But then the other thing it does is, again, it shows how the matrix multiplication is really a composition, right? I do one translation, and then I do a rotation, and so that's a composition. I'm taking the output of one transformation and putting it into another transformation to get a new output, and that's the idea of composition. And we did this with matrix multiplication and some vector addition, and so we see that composition at work. Okay, so I think that does everything we're going to do for section 2.2.